Today is the last day of this week. So we have been talking about one important application of lasers, which is nonlinear optics. So we have learned in the previous class under what condition one is stated to be in the nonlinear optical regime, and we also learned about the polarization that is created by intense light of laser, and we learned that this polarization created or induced. So we saw that the polarization that is created is given by the electric field of the laser and the electric susceptibility of different orders. So we learnt we further learned that these susceptibilities are tensor quantities of different ranks. So the proper way to write this expression is the following, and remember that P and E are the vectors. I am not writing the arrows, but you should remember that. And so on. Okay. So this far we have learned, and we also saw that with a couple of examples where nonlinearity in the optical properties is apparent, taking an example of absorption and refractive index. So now today we will be talking about one particular order of nonlinearity, optical nonlinearity, which is second order optical nonlinearity. Second order nonlinear optics is probably the simplest but most useful optical nonlinearity that people uses. Now from this expression you can find out about the order of different nonlinear processes. So the first term, of course, this is the linear process, that is the first order process, a linear process, and this is the term which corresponds to the second order nonlinear optical process. So if I write separately and I index this polarization by this term 2, which will signify this is a second order nonlinear process, then I can write, just isolate this, okay. Now if I ask you, this is a tensor, you probably now agree, okay, you should, because we have described why is it a tensor. Now if I ask you what rank of tensor, you should be also able to tell that, because you have already learned that in your plus 2 or in your undergraduate. So this is a third rank tensor, okay. So it is good to know, and this chi's will have several components depending on what rank of tensor it belongs to. So this is a third rank tensor, so you will have total 27 components, okay. So that will come from different ijk indices, okay, which corresponds to the Cartesian components. So now among this different possible second order nonlinear optical processes, what we can have, so the simplest yet most powerful is known as second harmonic generation. I have used this term quite a number of times, And now we will be talking about this one in bit detail, and we call in short SHG, second harmonic generation. The second order nonlinear optical process also consists of another process which is known as sum frequency generation. Also there can be a difference frequency generation. So, sum or difference frequency generation. This is in short called SFG for the sum frequency generation, and difference frequency generation is known as DFG. Okay. So, apart from these two most important processes, there is another one process which is known as parametric conversion. It is essentially optical parametric conversion. Okay. So, using these different second order nonlinear optical processes, we can convert frequencies. Okay. And this is essentially not a part of this course, but this is not only used for frequency conversion, but these processes are associated with certain properties of molecules, and they can tell us a lot about structure and property of different molecules and materials, and that is why these processes have tremendous importance. Okay. Now, we will next I will just mention here that the first process, second harmonic generation, this was first observed in the year 1961, and it was done on ruby laser. So, ruby laser has fundamental wavelength of 694.3 nanometer, and the second harmonic will be half of that. Okay. So, you can see I am calling it as a harmonic generation. So, this first term, if both the frequencies are same, then the resultant new wave will be called a second harmonic wave, and the incident photon, that is the E that we use to excite a material or allow the material to interact with it, is known as fundamental. And similarly, if I go to this process and if I choose my all the electric fields, that is E, J, K and L, to be originating from the same frequencies, then the yield will be another harmonic, and this is a third order process. So, it will be called a third harmonic, okay, and the process will be third harmonic generation. All right. So, now we will deal with the second order optical nonlinear processes. So, we should know the expression of this second order nonlinear optical processes, and with a special emphasis on this process, second harmonic generation. Okay. So, we will first look at the phenomenological expression for second harmonic generation. So, phenomenological expression of second order nonlinear optical processes, which involve laser radiation. So, let us consider. So, let us take this a laser beam, and consider it to be a plane wave. All of us are familiar with plane wave. Okay. So, we have learnt about it in high school physics. And let us also assume that this fundamental laser light, which is a plane wave, is characterized by a frequency omega 1 and an associated wave vector k1. Okay. So, these are the two things that characterizes my fundamental laser beam. Okay. So, the electric field associated with this, okay, when I am sending it to any material, so the electric field will be, so I will specify the position and the particular time. Okay. So, this one I can express as a function of omega 1 k1, right, and I have the phase as k1 and position as r. So, k1 r and the frequency is omega 1, fine. Now, in general, when I have to write, I take the complex conjugate of the electric field, so again omega 1 k1, and complex conjugate of the other part, that is minus k1 r minus omega 1 t. Okay. So, here there is no confusion, we already know these things. Okay. So, now if I want to write this exponential terms in terms of cosine, we can easily do that, and I will just write the form. So, sorry, this is omega 1 t, and in terms of cosine it will be k1 r minus omega 1 t, correct. And I can club this together and I can write in terms of a quantity E0 and the remaining fine. So, this is the form of the electric field of our chosen laser light, which is characterized by frequency omega 1 and wave vector k1. Now, this particular field, this will induce, what it will do? This will induce polarization at a frequency 2 omega 1, okay, because we are considering the process second harmonic generation essentially, okay, under the second order nonlinear optical process. So, if I want to make it general, then it will not be 2 omega 1, but it can be, if I use two different frequencies, say omega 1 and omega 2, then it will be in a combination of omega 1 and omega 2. So, is all I want to say that this particular field will induce polarization within a material which is suitable for nonlinear, showing nonlinear optical phenomena, and that polarization. So, this is not a general thing, but this is what we will end up with, okay, later on. So, this will create a nonlinear polarization. So, within nonlinear optical material, say it is a nonlinear optical crystal, fine. So, that particular polarization which we are talking about is also a function of the position and the time, and this one I have again the same way ijk and E, keeping it most general, and E k. Again remember, E and P are vectors. Okay. So, this is nothing new, we have already seen that. Okay. Now, I have the value for this electric field. Okay. So, that is the electric field corresponding to the laser beam, that is the fundamental light. Now, let us see, if I put this one here, what is the form of the second order nonlinear polarization with a most general term. Okay. So, let us just keep this part. Okay. So, essentially I have P2 as function of R and T is equals to this, that is that equation particularly, and these are also functions of R and T, okay, both this one as well as this one. Now, what we will do, we will put this value of E there. Okay. So, if I do that, what will I get? I will get this following. So, I have and I have E0 square cosine square k1r minus omega 1 t, correct. So, this is what we will get. Now, at this point, if I use the trigonometric identity, so what is the trigonometric identity? So, cos square x equals to 1 plus cosine of 2x this. If I use this, and we can rewrite this in a much simpler form. So, I will just write the final form. Okay. Plus and this is a function of the harmonic frequency as well as the wave vector multiplied by P0 square cosine so this is the final form of my P. Okay. So, if I just want to rewrite this one, so this is my P of R T and this is the second order nonlinear polarization. Okay. So, now there is a very interesting thing to note here, and so let me rub this one off. Okay. So, here this expression for the polarization, nonlinear polarization, second order nonlinear polarization has two parts. One is this first one and second one. So, the first one is frequency independent, okay. That is why this is 0. So, there are two parts coming from this equation. So, this one is frequency independent while this one is describing the result of a polarization created at the frequency which is twice that of the fundamental frequency. Fundamental frequency is omega 1 and this is a function of the double of the frequencies. So, this part is essentially the second order wave, or we can call it essentially the SHG wave, okay, which is characterized by this double frequency, double the fundamental frequency. And this one, which is frequency independent, is known as DC effect, because this is frequency independent. So now we have to elaborate with this part for the second harmonic generation process. Alright. So this second harmonic wave that will be created in this way, that can interfere either positively or negatively, meaning constructively or destructively. Okay. So and that can happen either microscopically or macroscopically. So this guy will lead to either macroscopic, if we are talking about a large system like a crystal, and for individual molecules it will be microscopic, right? Macroscopic or microscopic interference, and that can be constructive as well as destructive. Now if there is destructive interference, of course it is a problem. Now the thing is, the fundamental wave, it creates the polarization, that second harmonic frequency, and thus the second harmonic wave will be created. This fundamental and second harmonic, they will pass through the crystal, because I have a physical object, say a crystal, I am sending the fundamental, and then the fundamental is moving, and in the due process I have created the second harmonic. The second harmonic wave also will propagate through the crystal. Now while doing making this propagation through the material after the creation of second harmonic wave, this fundamental and second harmonic wave can pass in and out of phase, right. So the fundamental and SH wave will pass in and out of phases through the material. Say a nonlinear optical crystal. Okay. Now if they are in phase, well and good. If they are out of phase, then what will happen for out of phase movement? What I will get? I will get very low SHG. Okay. So one moment, I will just go back here. If you have any confusion why I am saying this one as SHG, I will just clarify for half a minute. This part refers to the second order polarization, no doubt about that, and a frequency which corresponds to double the fundamental frequency, and that is what is an harmonic, particularly second harmonic process. And when you have both the incident wave having the same frequency, this is what happens, and that is also characterized by this E0 square, okay, and that is why we have this process as second harmonic. Coming back here, so I cannot let this happen. So what I need to do is, we need to create a synchronization. A synchronization between the phase velocities of the fundamental and SH wave. Okay. So, why do we need to do that? Because there is something called dispersion, right? And because of this dispersion, I can have this, out of uh, out of phase relation between those, and can lead to destructive interference. So, I cannot let that happen, and I need to create a synchronization between those phase velocities. All right. So, and if I can do the synchronization, if I can have the synchronization, so that will essentially lead to maximization of second harmonic generation. Not too difficult to understand here, right? So, we have seen some kind of similar situation when we discussed about the laser process also. Okay, when we talked about the creation of one particular mode, developing high intensity of a particular mode in the laser. So, now this synchronization of phase velocities it has a particular name, and which is very, very important in case of nonlinear optics. And this necessity of having a synchronization between the phases of fundamental and harmonic waves is known as phase matching condition. Without having a phase matching condition fulfilled, there will be no appreciable nonlinear optical process, okay, be it second harmonic generation, some frequency generation, or any other nonlinear optical processes. So, in the next class we will be looking at this phase matching condition, what is the necessity a little bit more elaborately of phase matching condition, how to get that phase matching condition, okay, all those things, and I thank you for your attention.